Hi guys, welcome back. It's lesson 23, everything you ought, or ever wanted, to know about linear algebra in one lesson. First of all, I want to start out with notation. Now, you guys at this point are a little bit more familiar than the last year's troops were with the notation, but let's talk about it. We're going to have the notion of a column vector, which is also going to be thought of as a ket. So a ket, what we've been using as a ket, I want you to think of that as a vector of numbers. It's just a list of numbers, but it's a vertical list of numbers. And a bra is actually the adjoint of the ket, and it's a horizontal list of numbers, at least that's the convention. And the one difference between the bra and the ket is that in the bra version, everything is conjugated. It's complex conjugate of its value. The corresponding component of a bra is the complex conjugate of the corresponding component of the same ket. Okay, and then there's the idea of an inner product. Of course, an inner product is what you get when you dot a bra with a ket. And to calculate, sorry for my cough, I've got this terrible cold. I hope it doesn't cause you guys too much grief. I may have to re-record this after I recover, but anyway, the inner product is the bra times the ket, and the way you compute that is to multiply g star f for each element in each component and then add them all together. So that's the inner product. I want to point out something, that when you compute the inner product of g and f as a inner product, as a dot product, it's the complex conjugate of what you get if you compute the same inner product in the opposite order, f on g. To be a vector in a vector space, vectors have to obey normal rules of algebra. You need to be able to add them, multiply by complex conjugates, complex scalars, and then add them after you multiply by complex scalars. So it's the standard rules to be a vector space. You should check in Griffiths and see what the details of those rules are, but they're basically commonsensical rules of algebra that we already know. Okay, let's talk about basis vectors. So a set of basis vectors is sort of the analogy of the I hat, j hat, and k hat vectors from regular old vectors, spatial vectors. And so in linear algebra, we use basis vectors, which are sometimes called the e sub i's, e sub 1, e sub 2, e sub 3, e sub 4. And then you can write any ket as a superposition of complex numbers, the components, times the corresponding basis vectors. So one particularly nice orthonormal basis is the basis that looks like this: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. You can see quite trivially that if you compute the ket f at the top of the screen, you can think of that as f1 times e1, f2 times e2, f3 times e3, f4 times e4, and that obviously gives you back the column vector f1, f2, f3, f4, just like we said before. So that's one easy example. Of course, you can have other basis vectors that aren't quite so simple, but they still can be a legitimate basis. How do you find the components of any vector? Well, you take the inner product of that vector with the basis vector whose component you want. So for example, if you have a ket f, that's the superposition of 4 basis vectors, and you want to know what's the 2 component, then you could say, let's hit f with e2, and what are you going to get? Well, e2 on e1 is 0, e2 on e2 is 1, e2 on e3 is 0, and e2 on e4 is 0. And what's going to survive? Well, just the number f2. But that is exactly what we mean by the 2 component of the ket f. Notice that this is exactly like Fourier series. This is precisely the same calculation you do to get the coefficients or the components of a Fourier series. So there you go. You can think of vectors as pointers in an n-dimensional space. So just like spatial vectors with I hat, j hat, and k hat are pointers in a 3-dimensional space, you can think of these arbitrary kets as pointers of a kind in an n-dimensional space where n is the dimensionality of the ket. So how many components does it have? So for example, you can imagine a 9 ket. A a 9 vector, which has 9 components. And we could imagine thinking about that 9 vector in terms of a graph that gives you the value of each component. Notice that the F1 component is 0.2, the F2 component is 0.3, and so on, but that forms a kind of a graph. What if we had a 27 component vector or a 270 component vector? You can see that as the number of components goes up, the spacing between the bars gets closer and closer, and then you can see how we could take this concept into an infinitely large dimension, and you get an infinite component vector, which is also known as a function. Okay, so a function, one way to think about a function is as a vector, just like these other vectors, but with an infinite number of components, because the variable x, which labels the component, has a continuous set of values. Okay, so moving ahead. How does the inner product work with a very large dimensional vector? So with a 10 vector, you'd have an f vector that looks like this and a g vector that looks like this. What do we get when we take the inner product? Well, one way to look at that is as a bar graph. The f vector is the blue and the g vector is the green, and g on f is what you get when you multiply the corresponding values of the two vectors and add the result. So it's a sum over the components, and it ends up looking something like this. It's a summation over all I of g sub I star f sub I. What happens, and you can actually calculate that, boom, 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 you get a number. What happens if you take the limit as the number of components becomes very large and f and g become functions? What is the natural extension of this idea? Well, here's a 27 element version of the same idea. Notice that it's starting to look like the product of two functions. And what is the summing like? Well, the summing is like an integral. So the inner product for vectors in a functional vector space, a vector space of functions, the natural analogy, an analog of the inner product from the discrete vector space is the integral of g star f, which is exactly what we've been using. So that's how you might think about the meaning of the inner product for functions as elements of a vector space. Now, one other thing I want to point out, notice the dimensions of f and g in the discrete vector space are unitless, but in the function vector space, the functions are not unitless because we're integrating over space, and so that means the functions have to have units of 1 divided by the square root of length. So that's also true of our quantum mechanical wave functions. And the reason is so the inner product can be a unitless number, an amplitude. Okay, what's a linear transformation? A linear transformation is sometimes called a linear operator, but a transformation does things to vectors. So if you apply a transformation to a vector, what do you get? You get a new vector. If you O hat acting on the ket psi gives me a new ket phi. That's the idea. So linear transformations are special in that they act on a superposition of two kets. The result is the same as if you acted on the individual kets and then added them together. So in other words, if you have an operator O acting on a superposition, A psi plus B phi, that's the same as A times the operator acting on psi plus B times the operator acting on phi. So that's what we mean by a linear operator. Sometimes it's useful to imagine projecting out part of a system. So I want to talk about something called a projection operator. So you might say, for example, what part of a 4 vector lives in the E1, E2 plane? So you have a 4-element ket F, and we want to know what does that look like if we project it onto the E1, E2 plane? Well, clearly that's just going to be the 1 and 2 components are there, and the 3 and 4 components are missing. So that's the idea. Can we build an operator that does that? Is it possible to cook up an operator that does that? The answer is yeah. Let's look at an operator like this one. E1 as a ket times E1 as a bra. That turns out to be an operator. It's a special kind of operator called a dyad. But if you apply that operator to a ket F, what do you get? Well, E1 acting on F, we already know, projects out the F1 component. It's a scalar equal to F1, but the E1 basis vector is just the column with a 1 in the first slot and zeros in the other slot. So when you multiply that all out, you get F1, 0, 0, 0. So you've projected out the 1 component of F. You can do the same thing with E2. So the E1 projection operator projects out the 1 component. What does that guy do? Well, it projects out just the 2 component. And what do you get if you have this? E1, E1 plus E2, E2. Well, the first one projects out the 1 component, the second one projects out the 2 component, but then they're added together, so you get F1, F2. That's our desired projection operator. Hey, what about this guy? That's right, it projects out each of the 4 components and adds them back together. So if you apply this guy to any arbitrary ket, what do you get back? The same ket you had before. So this is also called the identity. This turns out to be one of the most profound theorems of linear algebra, that if you add projection operators together that project out all the different dimensions of your space and add them up, you get the identity. So anywhere in your problem where you don't know what to do, one trick is to insert the identity and magical things will happen. So let's try to figure out what linear operators do by determining what happens when you act on an arbitrary basis vector with a linear operator. It turns out, if you know what a linear operator does on all the basis vectors, then you can figure out what the linear operator does to any vector at all. Because, of course, any vector is a superposition of basis vectors, and so you're done. So that's the idea. Say we have an operator O, which produces a set of kets O sub I when it acts on the basis vectors. So like this. O acting on the E sub I basis vector produces a special new vector called O sub I. Okay, that's the idea. If we know what the O sub I are, we can figure out what the effect of O is on any basis vector, or on any vector at all, because you can see that O acting on an arbitrary vector, it can always be written as a superposition of basis vectors, is the same as the superposition of O acting on the individual basis vectors. And of course that's the same as the components of the original vector acting on the O sub I, multiplying by the O sub I. And how do we figure out what these O sub I are? Well, we can get the jth component of one of these O sub I's by taking the inner product of O sub I with E sub j. So here's the idea, E sub j acting on O sub I. But remember what the O sub I are. The O sub I are the O operator acting on the ith basis vector. So we can define O sub ji as the inner product of the jth basis vector with the result of O operating on the ith basis vector. That's kind of a mouthful. Okay, so let's get the components of the resulting object. So if O acts on F, that produces a ket G. E sub I acting on G is the same as E sub I acting on O acting on F. But how do we figure out what that is? Well, remember I said a lot of times if you don't know what to do next, just stick the identity in. Let's try it. We'll put in the identity between O and F, but then we'll rewrite the identity as the superposition of the projection operators of the entire basis, like that. Okay, I just replaced the identity with the sum over j of E sub j ket times E sub j bra. But the order of summation doesn't matter. I can take the inner product of the sum or the sum of the inner products. I'll get the same result. So we move that outside, and we see we have the following thing. The ith component of G is the superposition of Oj times the jth component of F. In other words, I can rewrite this as the product of the elements O sub ij acting on F sub j, summed over all j. Let's talk about the meaning of that. Actually, that is the definition of matrix multiplication. If you write out the components Oj as a matrix, and you imagine multiplying that matrix by the vector F, you'll notice that the vector G is nothing other than the matrix O operating on the vector F. So this is, in fact, what matrix multiplication is, and it turns out it's a simple consequence of putting the identity in to the definition of O. So there you go. Very exciting. Let's talk about changing a basis. Let's say we have some other basis. We have two sets of basis vector, the e's and the e primes, and we want to know what the components of F are in the e prime basis, assuming we know what the components of F are in the E basis. Again, the plan is to use the identity. We just write down that F is the identity operator acting on F. But what is the identity operator? Let's write it out in terms of the E sub i's. In other words, if we want to know the J prime component of F, we take the J prime component of I acting on F, but I, remember, is the sum over the E sub I basis. And so we can write that F, the J prime component, the prime component of F sub j, is the sum of these inner products between the basis vectors in the prime set and the unprimed basis vectors multiplied by the vector F. So let's see what that turns out to be. If we define Ej prime E sub I as the matrix elements of a transformation called T, we can write the change of basis as just a kind of transformation. It transforms vectors in the unprimed basis to vectors in the prime basis. So if we want to figure out how the basis vectors themselves transform, we can play the same trick, and we can see that what happens is the transformation that transforms the basis vectors is the transpose conjugate of T. And we're going to learn later that when you take the transpose conjugate of a matrix, what you get is called the adjoint. It's the adjoint of the matrix. Okay, let's just go over some terminology real quick. Transformations that take one orthonormal basis into another are called unitary. Under such transformations, inner products are preserved. So you can think of a unitary transformation as kind of like a rotation. It keeps the vectors' lengths the same, it keeps the angles between all vectors the same, but it just rotates them in some way. Okay? The inverse of a transformation has the property that if you apply a transformation and its inverse, you get the identity, or nothing happens. The transpose of a transformation is what you get when you interchange the rows and columns of the matrix. The conjugate is what you get when you take the complex conjugate of every element of a matrix. And the adjoint is what you get when you take the transpose and the conjugate. So we're going to find out later there's a different definition of adjoint, which is equivalent when talking about matrices, but it's a little more general because it applies to all linear transformations, whether you represent them as a matrix or not. Okay, a unitary transformation has the property that its inverse is the same as its adjoint. So in a unitary transformation, taking the adjoint and taking the inverse produces the same result. And finally, a Hermitian transformation, or sometimes it's called a self-adjoint transformation, has the property that its adjoint is the same as itself. Okay, and then as far as notation goes, we have a matrix A. We can talk about its transpose, that's A with a tilde on top of it. We can talk about its conjugate, which is what we get when we take a star. We complex conjugate every element of the vector. And its adjoint, we use a kind of a dagger symbol to represent the adjoint. Finally, the inverse is we take the power of -1. That doesn't mean we take the reciprocal of every element of the matrix. It means that we calculate the inverse of the matrix, which when matrix multiplied by the original matrix gives you the identity. Okay, so for board work today, we're going to be doing a rotation. We're going to treat the basis vectors of the original x and y axis and the basis vectors of the primed x and y axes as if they were two different bases, and they are, but we'll be using the notation and using the concepts from this lesson to calculate the transformation to convert a vector from one basis to the other basis, okay? And you'll probably recognize it when we're done, but we'll use the techniques described in this lesson to do that. And next time we'll move on and talk about eigenvalues. That's it for today.